Okay, time to begin.
No.
I'm going to finish up just one topic really on fluids, and then I'm going to try to do an abbreviated thermodynamics because we are behind. I've been way too slow in going through this fluid section, which makes me sad. So it was, I believe, Daniel Bernoulli. I think it says in the same on the next slide the actual name of the gentleman who noted that pressure changes with speed in a fluid. You remember my little demonstration? I'll do it again because it's just so nifty. With the blow dryer, right?
Yeah.
Anybody have any idea why it did what it did?
Because the air is still enough to hold it up.
Clearly, it's not over the blow dryer here. So how can that hold it up? And Bernoulli is the one that gave us the answer to that. What he determined was when a fluid flows faster, the pressure drops. So with the blow dryer, I'm blowing air faster than the air in the room, right? And so that makes the pressure in the stream of air lower than the pressure in the air around it. Now, pressure is force over area. So if we take a ball and we blow air on it, because of its weight, it will go down to the bottom part of the airstream. Just its weight will bring it down. So it'll have air blowing over the top, but not under the bottom. And so then if we look at the forces, since the force is always going to be pushing in, the forces on top pushing down to the air pressure are going to be lower because the pressure in the moving air is lower. And so you have a higher pressure underneath, more force pushing up, a lower pressure on top, less force pushing down. And just like we saw with yesterday's experiments in buoyancy, that's going to give it a net upward force to counter gravity and allow it to stay in the air until you get it tipped out far enough that the upward force isn't enough, because you also had air blowing and pushing, giving it some upward part there. So if you do it right, you can lift things up. So if I take one of these and I put it over the edge of the desk here, of course it sags down because of gravity. What should happen if I blow air over the top? It pulls it up, right? A little too violently there. That's got to get your position right so it pulls it up, but doesn't pull up too hard. It's the same thing. It's because the faster the air is moving, the lower the pressure. When I was working at a Department of Energy lab, my last few months in graduate school, the last 9 months, we had to have safety lectures every month. The government required it. But they didn't care what the safety was about, and so we had a trained safety lecture in a science lab. And they showed us video after video of people who do stupid things and get hit by trains. And one of the common ones is, hey, look, here's a train track. I'm going to stand this close to the train track. Well, yeah, the train's going to pass this close. The train's not going to hit me. I should be fine, right? But when the train comes, it's pulling air with it. And because it's pulling air with it, you have moving air. What does that do to the pressure of that air? It makes it lower. So now you have higher pressure behind you and lower pressure in front, and the air pushes you into the train. And then you go funk and it's all not fun.
I don't think you know it's not fun.
What?
I don't think at that point you would know if it was not fun or not.
That's probably true. So this is something that's really important. Yes, Daniel Bernoulli, 15th century Swiss scientist. So let's have our first clicker question about this. Are you putting in an answer, Haley? I still don't have an answer from you. Yeah. Can you do it again because it didn't register? Still not registering. All this because I don't want her to lose points. I'm sorry. Well, it's everyone. Oh, wait. I'm looking at Mecky and saying Haley.
Yeah.
My bad. Still wanting her to get her points. Sorry, Maggie. Any luck there? Okay. Everybody's in. 12 said pressure is higher. 6 said pressure is lower. Despite our time rush, the learning here, I think, is good when you talk to your neighbors to discuss why you answered. So go ahead and talk to your neighbor about your answer and what your reasoning is.
I read it smaller. I believe honestly, I was like, my dress, because I have like half an hour required trip today. It's in Lincoln. So I would be like, here's something out, like, my teaching lecture. Although I think it would be.
You can't answer yet, but I will in just a second. Okay, let's go ahead and answer again and see. So it's open now for you to answer a second time. See how you answer after the discussion. Not very funny, actually, now that I laughed. Okay. Make sure we're all in. So Eric and Candace, who are discussing it like good students, mind you. When you don't have it in because you're still discussing like you're supposed to, that's not the worst thing in the world. In fact, it's a good thing. You're gonna. Okay. So this time it changed to 15 and 3. Now we see how Brandon feels about this.
Okay, so I put C. In the book here, it says internal pressure is greater on slower moving water. And so it says that it's moving from the wide to the narrow, which means it's speeding up. And so if it's speeding up, then the pressure should be lower.
Okay, perfect answer. Thank you for being brave and wise. Brave because you went against the popular opinion. Wise because you also had the right answer and you stuck with your feeling. So he's absolutely correct. He even has his references there. As it goes from the fatter to the thinner region, the same water has to get through a smaller region, so it's going to have to go faster to get through. And so the speed goes faster when it goes into the smaller region, which then lowers the pressure because of Bernoulli principle. It's kind of funny because when I was taking my EMT class, actually it was after I'd passed the EMT class and was taking a refresher, the teacher called on me because I'm a physicist, and he says, when the blood vessels constrict, that raises the pressure in the vessels, right? And I said, well, no. Because when the blood vessels constrict, what does that do to the speed of the blood going through them? It raises it, makes it go faster, and when it goes faster, what happens to the pressure? It decreases. And so why, when we go into shock, do we have vasoconstriction? If you put more resistance to the flow, what's going to happen to the pressure on the other side where it's still big? It's going to go up because it's harder to get it through the smaller vessels. So the pressure goes down in the constricted vessels, but it makes it go up back toward the heart so that the heart can maintain pressure. And that's why the body is doing the constriction of the blood vessels. So the opposite is true. When I had pulmonary emboli, the pressure in the right side of my heart was like 3 times higher than it's supposed to be. And so they were giving me things to make my vessels expand so the blood would go easier through them so the pressure would drop. They didn't put me on Viagra. That is their best vasodilator. Just for the little history here, Viagra, when it was being tested for a vasodilator, something to relieve things like angina, people noticed a different effect. And the drug manufacturer said, ooh, we could make a lot more money selling it for that effect than we can for people with bad hearts, because recreation versus life, recreation comes out ahead every time, which is crazy, but true. So that's why they have those warnings about if you take blood pressure meds, you shouldn't take it when you watch the TV commercials, because it will lower your blood pressure. If you're already taking something to, work on your blood pressure, well, that could work against you. Application of the Bernoulli principle, really important. We live out here in the Midwest. And as I alluded to earlier, lots of people get relocated to Nebraska if they immigrate to the United States because people move away from here. By the way, I did look at a list. California is number 1 for immigrants. Nebraska is number 9. The other state that I've lived in, Washington, is number 4. So I've lived in lots of states that accept immigrants. It makes me proud. And of course, probably all of us can trace our ancestry to immigrants, right?
Unless we're all full Native American. Unless you're full Native American.
Yes, unless you're full Native American. But even then, the Native Americans are immigrants. Right? I mean, we're not a history class, but you should know that as far as we know, they came over a land bridge from Siberia, and they were probably Asians who came over land bridge and migrated south, going all the way down to South America. So we're all immigrants in this continent, even the Native Americans. Out here in the Midwest, we have tornadoes. And tornadoes are scary things. And when a tornado comes, one of the things that it can do that's scary is to take your roof away. Because you have high-speed winds going over the top of the roof, and inside the house you have still air. The high-speed winds over the roof means the pressure over the roof is lower. So you have the air inside the house will pop the roof off because of the low pressure above. And so, that's a problem. And it happens to houses. That's why cars can get lifted up by a tornado. Those high winds lower the pressure above it, up it goes. Airplanes fly for the same reason. When I was in graduate school, I thought it was just funny to sit and talk to the people in the airplane and explain to them how an airplane flies, because before you know how it flies, you just trust they've got this thing figured out. But then when you understand how it works, it becomes a little scarier because it seems so tenuous. The airplane wing is designed so the top part is longer than the bottom. It has a curvature. There's 2 things you worry about. One is the attack angle. You notice this thing has a general downward slope. That's the attack angle. So air that hits it on the bottom will bounce down. Conservation momentum means that there was a downward force on that air, which means there had to be an equal and opposite upward force on the wing. But you also have that the top is curved much more than the bottom, so that the distance air has to travel over the top of the wing is a longer distance than it has to travel under the bottom. Now, as the airplane's going through air, the air molecules basically just go like this. So the time for an air molecule to go from the beginning of the wing to the end of the wing is the same whether it's top or bottom, but it covers more distance on the top. Hence, the speed of the air relative to the wing is faster on top. And if the speed is faster on top, what does that tell you about the pressure? Pressure is lower on top, pressure is higher on bottom. And it's that pressure difference that gives us the force we call the lift force, the force that holds the airplane up in the air. And when you understand, wow, so it's just that subtle difference in length of the wing that makes the wind speed a little bit lower on top that's lifting this thing up, it becomes a little scarier, right? Or yeah, it does to me. So that's how airplanes fly. They take advantage of this Bernoulli principle. Can you think of something else that might take advantage of this Bernoulli principle? A bird. Well, as we learned yesterday from our esteemed lab TA, he was lying to students because he was joking. He said that the shape of a bird is lighter, and that's why they fly.
He said the shape of a bird is what makes the difference.
Yeah, and it's not the shape, but it is the shape of the wing, because when it's going through the air, its wings are once again shaped something like this, so that it has higher speed on top and gets some lift. Any other examples before I move on? A windmill? Windmills are a little different. They use something that air just hits for the most part. There are some windmills that do use this, but they're not as common. What I was thinking, well, what I think, because I think sailing's cool, is sails. The sail on a boat is doing the same thing. Now, if you lived 500 years ago, they would make a sail so it goes like this to catch the wind. And in that situation, the fastest you could ever conceivably go would be the same speed as the wind, because you're just being pushed by the wind. But in today's sailboats, they don't make the sails like that. They make the sails so they are something like, see, the wind's blowing that way, so something like this. And so the wind on this side kind of makes a pocket and goes straight across, and on the other side, it goes a bigger distance, it's faster. And then you're getting a force to push the boat rather than just the wind speed. And so with the sail design like that, you can actually make the boat go faster than the wind speed, because you have a force pushing you forward due to the pressure difference, and then you have the resistive force of the boat going through the water. So does anybody here watch like America's Cup races? These days it's gotten really crazy. They use catamarans because they spread out their hole and they have two smaller holes instead of one big one, because that gives them less resistance in the water. Furthermore, they have little hydrofoils that they will use to lift the holes out of the water when they're going at speed. It basically has a little wing that's going through the water. That's what the hydrofoil is. And then they have very, very little resistance to the water, which means there's very little force slowing them down, and they have the huge force from the wind pushing them forward, and they can go extremely fast. So, this technology is used there. If you use like perfume, you've got the little squirt bottle and you go, right? It does when I do it. Okay, no, you go like this. You go, and you walk into it, right? That's how it works. Okay, what you're doing is you have a little tube that goes into the perfume, and then you have this attached to it. You squeeze this, and it forces air to go like this. But if that air is going across, the pressure is lower. And so the lower pressure makes the air pressure that is inside your perfume push perfume up into that, and then the perfume comes out with the air. So it's a really ingenious way of getting that perfume out, which is cool because science is cool. Okay, now we're getting into thermodynamics. Temperature. I've already told you that temperature is a measurement that tells us about the average kinetic energy of molecules. So here we have different things about temperature. Something you already knew. The number corresponds to how warm or cold something is. Low temperature is cold. High temperature is hot. But things you may not know is that there is no upper limit to temperature. Temperature could be millions, but there is a definite lower limit. We call that absolute zero, which I'll talk about in just a little bit. And absolute zero is, we use the Fahrenheit system here, right? It's around minus 460 Fahrenheit. It's not exactly minus 460. It's like minus 458 point something. I don't remember the number. It's probably on the few slides later. Or if you use Celsius, anyone here from a region that uses Celsius? That'd be any region but the United States and 2 other countries in the world. Truly, there are only 3 countries in the world that use Fahrenheit instead of Celsius. Why? I'll tell you why. If you watch Big Bang Theory, you'll know why. Well, if you watch it and you pay attention, you actually knew what Sheldon was ranting about. Back when I was a child, we officially changed to the metric system. And so the road signs were changed to kilometers. Well, they had kilometers and miles together. So it'd have like 2 speed limits, 1 kilometers per hour, 1 miles per hour, 2 distances to every location, 1 kilometers, 1 miles. And you know what? Well, I say my fellow Americans, but they were older than me. They, to you, they'd be people my age. But the Americans said, that's confusing. And so Jimmy Carter made a decision to go back to using the imperial system. We started the process. It wasn't comfortable. On the same note, you guys all know how to touch type probably, right? On a typewriter? Mm-hmm. That system was designed as a fairly non-efficient system to type. One story is that it was to keep teletype machines from getting jammed. And so there are better designed keyboards, the Dvorak keyboard. I know if it was music, you'd call it Dvorak. Dvorak keyboard or Colmac keyboard that are designed that are much more ergonomic. You can type faster with less errors. But everyone's afraid to change over because we have to learn something new. It's a human frailty. So that's a long answer to your question of why. In Celsius, it's minus 273.15 degrees Celsius. Those are the absolute minimum. Can't get colder than that. What causes temperature? I said that it's the average kinetic energy. Well, kinetic energy can be in different kinds of things. You have translational motion, that's stuff moving back and forth. You also have rotation, things rotating, and vibration going like this. And those combine to give us the total, what we call internal energy of a substance. So if I talk about the internal energy of the water, that's going to be adding up the motion energy, the rotational energy, and the vibrational energy. If you have something that's hot, it's probably going to have stuff moving fast. And so it'd be in the gas phase when it's hot because you have fast gas molecules bouncing to and fro. The difference between gas and liquid, gas is what we have in the air, right? In liquid, when you slow down the kinetic energy enough, molecules start to stick together. And it's lower energy for them to stick together. And so a liquid, you just don't have the molecules going fast enough to break away from each other. If you cool down even more, you can freeze. Freezing is when they've slowed down enough that they can pack together. You guys see, I've got this box of ping pong balls. The ping pong balls are all nicely sitting in a fixed position. That's the way a solid is. The atoms are sitting in a fixed position. But if I shake this, they'll start moving around. They're still in the box, but they're moving around. That's what a liquid's like. And if I shake it really hard, they'll start coming out of the box. That's what a gas is like. So the difference between those phases is simply about the average kinetic energy, or the temperature. Now, we measure thermometers a lot of different ways. But most of what you're used to is measuring something that expands when it's heated or contracts when cooled. And so, like when I was a kid, we used mercury thermometers. And for physics, we usually still do, but because of the mercury problem I mentioned in the last class period, we now are just using alcohol thermometers. So instead of mercury, we have alcohol with food coloring in it. That alcohol, when you heat it up, it expands and moves up the tube. When you cool it down, it contracts and moves down the tube. So we're just looking at expansion. But there are other ways. So I have some sensors that I can use, and I could point to a student and it tell me what their temperature is because it's looking at the radiation they give off. Believe it or not, all of us glow. The problem is we don't glow in the visible spectrum. So you guys didn't live through, the Gulf War and whatnot, but you turn on the TV and they show you night vision views of what was going on in Baghdad. and you see somebody run across the street, and then you see a building that just becomes a big bright blur because it blew up. What they're doing is they're looking at the radiation that things are giving off because of their temperature. And the actual wavelength, which we'll talk about next week, it turns out, depends on the temperature. So you can look at the wavelengths coming off an object and determine its temperature. So that's what the infrared thermometer is doing. It's looking at the radiation your body gives off to measure your temperature. One last one. Okay, so the infrared one, like they stick it in your ear and they tell you what the temperature is. It's looking at the radiation that was coming from your skin. Another type, they can just put a little strip on your forehead. Anyone had that? Put a little strip on the forehead, and it's got little things that change colors to tell you the temperature. No? Those are thermally reactive materials. They change temperature or change color with temperature. And so they put it on there and changes color with temperature so you can see what your temperature is. So here is the two common temperature scales, Fahrenheit and Celsius. Gabriel Fahrenheit, German dude. He, let's see, I'm quarter German, so I could be proud of that, right? Quarter? Mom is half. Yeah, makes me quarter. He developed a temperature scale that was based on two repeatable measurements, kinda. What they were is not very clear. I've seen different definitions, but the most common is he defined 0 degrees Fahrenheit to be the temperature of the ice and ocean water near his home, and 100 degrees Fahrenheit to be the body temperature of a cow. Now, that's a difference of 100 degrees between 0 and 100, and so that's what we would call a centigrade scale. Most people never think of Fahrenheit as centigrade, but centi means 100, so there's 100 gradients in the scale. It's centigrade. The problem with his scale was it depends on what's in the salt water, the ocean water. You go a different place and you have a different concentration of salts and minerals, and the freezing temperature is different. And likewise, a cow's body temperature changes. I mean, when I was working at the dairy, we would say they're in heat when they're ovulating. Why? Because their body temperature changed, and that was how we would determine when they were ovulating. So body temperature changes, so that wasn't a very good calibration. So then we go to Anders Celsius, a Swede. I'm also quarter Swedish. So, I'm torn between these two. And Anders Celsius said, let's use the freezing temperature of pure water at 1 atmosphere pressure. He said, let's make the freezing temperature 100 degrees Celsius. And let's make the boiling temperature of pure water at 1 atmosphere 0 degrees Celsius. No one here is correcting me. That's the way he set it up. He set it up backward. He died like a couple years later. So he came up with this like in 1742. He died a couple years later, and everybody said, well, that's ridiculous. Turned it over.
The moment he died.
Huh?
The moment he died.
I'm sure it wasn't the moment, but they waited until after he died at least. So now 0 degrees Celsius is the temperature of freezing water. And the Celsius scale has been recalibrated to be based off of the Fahrenheit has been recalibrated to be based off the Celsius. So 0 degrees Celsius is exactly 32 degrees Fahrenheit. And 100 degrees Celsius is the boiling temperature of pure water at 1 atmosphere. And that is exactly 212 Fahrenheit. But of course, 32 to 212, that's a difference of 180 degrees between the new calibration points. So with its new calibration, it's no longer centigrade. Whereas the Celsius scale, as I defined it, is, but that's not how it's defined anymore either. Back in the 70s, they shifted from a centigrade scale to going from the triple point temperature of water, which is 0.01 degrees Celsius. Triple point means you have ice, water, and gas all at the same temperature and pressure. And there's only one temperature where that can occur. So they use that for calibration point. Why? Because it's very, very, very perfectly reproducible. You can do it. You can calibrate anywhere in the world. So those are the temperature scales that we use today. And like I said, all but 3 countries are going to be using that one. Our country, okay, that one. This one here. Well, nope. This one. Yeah, there we go. Our country uses Fahrenheit. In physics, we'll use Celsius. So here is just some ideas of different temperatures. The lowest possible temperature we call absolute zero. 0 kelvins. Kelvin is a scale that is just set so 0 will be absolute zero. Since there is a minimum, let's set it to 0 to make life easy. And so the difference between Kelvin and Celsius is the temperature in Kelvin is equal to the temperature in Celsius plus 273.15. As you go up, you'll notice we have the temperature where water freezes and boils. Keep going up, you have the surface of the sun, not the core of the sun. Surface of the sun is about 6,000 kelvins. That's hot, right? Notice temperatures for things to melt. Iron melts up here at 1,800. So iron's a high melting temperature. Pretty much everything would be melted and vaporized, and indeed it is, in the sun. Sing well. You go further, surface of a hot star, center of the sun. Center of the sun is about 20 million kelvins. Yeah, I've heard more like 16 million kelvins, but between friends, I think they rounded. And a hydrogen bomb, 100 million kelvins, right? There's no upper limit on temperature. You can get hotter and hotter and hotter, but there's an absolute minimum for cold. What happens if you were to cool something to absolute zero? It what? It would break? Okay. In theory, depends on the material if it would break, but in theory at absolute zero, all motion would cease. It would come to a stop. All molecules would stop. Remember I said a solid, they're at fixed place like this? But they're still doing tiny little vibrations in those fixed positions. But if you got down to absolute zero, in theory, they would stop. Quantum mechanics says they can't quite stop, but it's slowed down as much as is possible. Now, heat. Heat is a very misunderstood word. Sometimes people think heat is the same thing as temperature. It's not. It's not the same type of thing as temperature, but it's related. Heat is a flow of energy. That brings the second misconception. A lot of people think heat is the same as energy. And so they'll say, how much heat is in this cup of water? And that's a nonsensical statement. I forgot what it was, but I was reading something in a science article, not a physics article, mind you, that talked about the heat that was in something. Doesn't have heat. You can't possess heat. Your body is warm, you possess internal energy. Heat would be a transfer of that energy. So heat's a transfer process. And if heat goes into you, your temperature goes up. If heat goes out of you, your temperature goes down. So there's a relationship, and that's why they get confused. But heat and temperature, two different things. The units for heat. If heat is energy, what's the unit we use for energy? Joules is the unit we use for energy. But before it was understood what heat was, people thought that heat was a fluid that flowed. Right? They knew it was a flow that had to do with energy, but they thought it was a fluid. And so there was a theory of the frigidic, which was a fluid that would flow and bring cold to things, and a theory of the caloric, what was a fluid that would flow and bring warmth to things. But then, I don't remember which scientist it was, but a scientist was working on drilling cannons and noticed that, the cannons get really hot when you're drilling them. But if you stop the drilling, it stops. And he said, maybe it's the work I'm doing drilling, work is transferring energy, that is causing them to get hot. So instead of it being a fluid that's flowing, it's simply the work that I did. And so then we had Joule, is it James? I don't remember his first name, so I'm not going to. I think it's James Prescott Joule, but I could be wrong, did an actual experiment where he measured how much work he did on water and how much his temperature increased. And from that, he calculated the relationship between the heat and the work. And so that set a relationship that 1 calorie of heat is 4.19 joules. If you want to be more specific, 1 calorie is equal to 4.186 joules. Some textbooks use different numbers. It's really confusing, so don't get hung up on that. So a joule is a measurement of how much energy is transferred. A calorie is defined as how much heat you have to transfer to raise 1 gram of water, 1 degree Celsius. That's what a calorie is. Now, of course, you've all heard of calories. Sometimes I count them. When I'm counting calories, I'm counting, what am I counting?
Energy.
I'm counting the energy that I'm eating. And so the calorie is a measurement of the energy that I'm eating. Now, the calorie that you count when you're on a diet is not the same calorie I just described, but it's really, really close. The dietary calorie is a kilocalorie. What does kilo mean? 1,000. So 1 dietary calorie is 1,000 calories. Now, that can confuse even the most wise. Capital C is a dietary calorie, and that's 1,000 lowercase c calories. So when you eat a candy bar and it says 220 calories, that means you have enough energy in this candy bar to raise 1 gram of water by 220 degrees Celsius. That's a big energy, right? There's a huge amount of energy in a candy bar. How do scientists know how much energy it has? They make this thing we call a bomb calorimeter. It's a bomb calorimeter because what they do is they take a strong metal chamber and they put the sample they want to measure how much energy it has in there with a little filament that will start a fire and then fill it with oxygen, which is a good oxidizer, so it'll burn. And so they might take a little piece of cake, put it in there, put the filament, fill it up with oxygen and seal it, then they put it in water, then they send a little electricity through that filament to make it burn. And that cake burns, and they measure how much the water was heated by that burning cake, and they say that's how many calories it had. Right? It's a very practical measurement. Our bodies use energy just the same way that fire will convert energy. So now that doesn't mean that we can eat everything that burns. For instance, wood. That the wood fiber our bodies can't digest. So yeah, there's calories there, but not calories that we're going to be worried about. And that's why they put it in your cheese when you get low-fat cheese. Right? They put basically sawdust in there, and you can't digest it. Does that make you happy? Yeah, me either. Okay, so I'm just going to go past that. Laws of thermodynamics. We have 3, and only 3, laws of thermodynamics. And so we're like, yeah, 3 laws. The first law says that when heat flows into a system, its energy goes up. When heat flows out, its energy goes down. And in fact, you cannot create or destroy energy. So that's the first law of thermodynamics. Energy can't be created or destroyed. So if heat flows into something, its internal energy goes up, which means its temperature is going to go up. If heat flows out, its temperature goes down. If you do work on it, that's energy going in, its temperature is going to go up. If work is done by it, its temperature goes down. That's what the first law says. So, succinct statement, energy cannot be created or destroyed. The second most succinct statement is to write this equation. which is just an energy balance. The change in energy is the heat you add minus the work done by it. Don't worry about the sign thing here. It's simply saying you can't create or destroy energy, and it gives you a mathematical relationship for it. So that's the first law of thermodynamics. Now, after the first law was devised, scientists realized there's a more fundamental law that they should have devised. There's a fourth law. Ah, shoot. We have 3 laws, but then they said, there's another one that's more fundamental. They call it the zeroth law. And that zeroth law says if temperature 1 is equal to temperature 2 and temperature 2 is equal to temperature 3, then temperature 1 is temperature 3. Shocking, isn't it? That's like saying if Vanessa has the same amount of money as Brandon and Brandon has the same amount of money as I do, then I have the same amount of money as Vanessa has. It seems really obvious. The thing is, the more they studied thermodynamics, they came to realize that temperature was a more complicated thing than they initially thought. And it turned out that it wasn't obvious because of what temperature really is measuring. So that's the zeroth law. It's not even mentioned, I don't think, in your textbook. First law, energy can't be created or destroyed. The second law tells us the direction that energy flows. Heat, specifically. Heat is a transfer of energy because of a temperature difference. It doesn't involve motion like work does. Work, you have to have a force and a distance parallel to that. But heat, just a temperature difference. And the second law of thermodynamics says that heat will always flow from a hotter object to a cooler object. And so it gives us the direction that things go. We sometimes call this second law times arrow because it's the only law in physics that tells us what direction something's going to happen. Except for that second law of thermodynamics, I could say this here is sitting on the tabletop. And then it's perfectly possible for the tabletop to cool down, transfer energy to that, and this thing to fly up in the air. That doesn't violate anything except the second law of thermodynamics that says that heat cannot flow from a colder region to a warmer region. Now, this here is a trick thing. I turn it inside out. I have to push on it. I do work to turn it inside out. And then I set it on the tabletop. And at some point in time, it's going to return the potential energy it's storing. So it's storing potential energy. What's going to happen when it returns it? Yeah. Okay. Third law of thermodynamics. It's going to scare me. The third law of thermodynamics says that nothing can reach absolute zero. I said earlier, what would theoretically happen if we reached absolute zero? The third law says it can't happen. And we can use the second law to make a good argument for why. The second law says that heat naturally flows from hot to cold. So if I want to cool something down, I have to remove the heat. So I have to make something colder to cool it down. Well, that means if I'm going to make something cool down to absolute zero, I have to have something that's colder than absolute zero. But since there's nothing colder, you can't do it. So we can get things arbitrarily close to absolute zero, like 0.000001 kelvins, but we can't get it to absolute zero. And they do that actually with what we call things like laser cooling, where you use a laser beam to slow down the motion of the molecules. Okay, second clicker question. When work is done on a system compressing air in a tire pump, the temperature of the system will do what? So you're compressing it. I will start you out. When you're compressing it, you are doing work on it. What does it mean to do work on it? Okay, force over distance. But if you're doing work, remember Casey and I were talking about me doing work and her absorbing. Doing work means you're adding energy. So the key here is you're adding energy by compressing the air. What's that going to do to the temperature? There it goes. Okay, everyone but Hannah. All right, so here we had pretty good agreement. 14 said that when you put energy in, the temperature goes up. Yeah. Let's call on someone. Just Candace. Did you agree with that? Why?
Because heat is the flow of the energy. So there's obviously a flow of energy when you're working on something. I don't know.
Okay, now your answer had some right and had some wrong. Heat is a flow of energy. Absolutely true. Work is also a flow of energy. There are two different ways we can have energy flow, heat or work. But in both cases, if you have energy flow in, then you have an increase in the internal energy and it gets hotter. So you had the ultimate idea right. It was just mixing the two different types of heat flow. Good job. Can I repeat what I said? Yes, that there are two different types of energy flow. There is heat, which is energy flow, does involve motions just because of a temperature difference. And there's work that involves motion. You have a force and a distance it moves. Either one of those will transfer energy. And if you transfer energy in, the temperature goes up. Now, entropy is a measurement, we commonly call it disorder. It really is a measurement telling us about how likely something is. The higher the entropy, the more likely it is. And so things naturally go to higher entropy because they're going to the more likely states. I'm going to go past this to talk about thermal expansion in our last few minutes. So thermal expansion. When we heat something up, the molecules go faster. Let us imagine that we were all standing in the room and we had all the tables out of here, which we can't do. If we're going really slow, in terms of temperature, what would that correspond to? Low temperature. And if we're going really slow when we hit each other, we just mildly move away from each other. No big deal. But if we were going fast, what would happen? We'd bounce off hard, and we would start to spread out and get farther apart from each other. And if we consider ourselves one object, what would be happening to our size as we go faster? Would be expanding, right? That's what happens with virtually everything. And so here's an example. I have a ball and a ring, and you can see pictures of this in the textbook. The ball fits through the ring. If I heat up the ball, what should happen? It should get bigger. Now I'm not heating this up, so the ball should be getting bigger, and it takes a while. If I put it right now, you won't notice anything. But it's going to heat up and get bigger. What do you suppose will happen when I let it heat up enough? It won't fit through. So I'm always impatient. I have to try, and then it fits through, and I have to heat it up some more, and I feel stupid. But, okay, barely fit through. Got to heat it up some more because I feel stupid. We got that straightened out, right? So wait a minute. While this is doing that, I'm going to do something else. I'm going to put this in here too. What's this?
I can't see it.
It's something that's a little piece of metal. Put it in the flame. And what's it doing?
Bending.
Now, why in the world would it bend?
Because it can't anywhere to go.
I take it out of the flame, and what's it doing? It's straightening out again. Something about temperature made it change its shape. Okay, now it won't fit through. How can I make it fit through? Heat them up together. Heat them up together, then the ring will expand. The hole in the ring will expand. Come on, expand some, baby. Believe me, it'll expand. I don't have time for this.
Yay!
Yay! Expand enough for me to get through once. Okay. There we go. Now it fits through easily. Now this is always cool. What happened there?
The energy went out really quickly.
Energy went out really quickly, heated up the water really quickly, made it boil, and you heard the gas expanding. Okay, this here, the reason it did what it did is because it's actually two different types of metal that are bonded together. And one expands more when you heat it than the other does. And so the one that expands more is on the outside and makes it curl. So you might see things like these things on bridges. Those are expansion joints because if you don't put them there, when it gets hot, the bridge expands and it would buckle. Or when it gets cold, the bridge would contract and tear itself apart. So you have those so that thermal expansion doesn't cause a problem. This here is an example of train tracks that did not have enough expansion space and they curved, buckled because of the stress when they were heated up.